superconducting twisted van der Waals heterostructures.
Yeah.
Nicola, please.
I changed a little bit the title, but yes, basically, yes, it's that. So, thank you. Thank you for the organizers and the chairman to give me the possibility to give this talk. And so this is the outline of the talk, and I will talk about, first of all, an example of pair-time symmetry breaking, the dynamic mode transitions, and can we expect theoretically parity time or time-broken symmetry states from a twisted coupled heterostructures? Why these twisted coupled heterostructures are so difficult to make? The problem of the oxygen, and measuring the Josephson coupling between twisted coupled heterostructure. I will show some data in experiments. Then with the detection of the second harmonic modulation in the Josephson effect at very high temperature and specific angle in these devices. And further work also is in progress to the topological state in those systems. And also some recent results towards the integration of hybrid superconducting and thermal circuit with exotic mechanical and electronic properties of twisted coupled heterostructures. So I would like to thank, first of all, my group, and Christian Sangao, Tommaso Confalone, Miki Martini, Sana Shokri, Yejin Lee from the FW-Dresden, and also from visiting PhD student from the University of Napoli, Giuseppe Serpico, and Aulin from the Max Planck Institute. And also the collaborators, Cornelius Nisch, Valer Vinocourt, and Domenico Montemuro, Francesco Tafuri, Valentina Brosco, Uri Vol, Gendagu, of course, that provides the crystal that we are going to use, Kenji Watanabe, Takashi Taniguchi, Philip Kim, and Pavel Volkov. And also some special thanks for people and technicians that helped me on this way. So now, even if you use a single superconductor, like a conventional niobium structure, depending on how you realize the architecture, you can get very exotic state. So the architecture is fundamental in geometry. In this case, what you see is 90,000 Josephson junctions are organized in a square lattice of proximity superconducting island on top of a gold substrate. What happens if you apply a magnetic field perpendicular to this kind of a system architecture is that you will form a Josephson vortex that you see on the right. A Josephson vortex which will start to move on one direction across the islands. Now, of course, this is happens that when you move the system to an equilibrium state, so you can think about this Josephson vortex to some extent also like atoms in an ultra-cold atom optical lattice. So if you apply a current, then what you will see is that this system goes in an unequilibrium state. And depending on the current that you apply and the magnetic field that you apply, you can basically move the system from a vortex mode insulating state. There you see the differential resistance and the filling factor on the x-axis, which tells you basically how many Josephson vortices in which kind of crystallographic configuration are organized in your superconducting array. So you will have, in this case, with one Josephson vortex for each plaquette of superconducting islands. Then you can move the system from a non-equilibrium state, that is the vortex mode insulator, to another non-equilibrium state, which is the vortex metal, or a responsive metallic of the vortex lattice. And you can do the scaling, and what you discover is that you are basically in the liquid-gas transition universality class, or in the mode class at finite temperature. And then if you you can also describe the dynamic mode transition as a parity time symmetry breaking phase transition, with the mode insulating state corresponding to a regime of Hamburgian parity symmetry with a real energy spectrum. So this experiment has been reproduced also in different configuration, and in this case is a triangular superconducting island proximity array. And the results are similar. So the dynamic vortex mode transition has been observed in multiple configurations. Now, we know so that the architecture is very important and can determine novel phenomena even if you play with the same material. So it is known from a long time that cuprates, and especially the BISCO, as we have this morning, they have, by spectroscopy, thermodynamics, scanning tunneling microscopy, the wave gaps. And the wave order parameters. So it is also known, and people have proposed and have thought for a very long time, how to exploit these nodal properties of this material to create interesting system. Now, one aspect that has been considered in the past is that there is a proposed inhibition of node-to-node quasi-particle tunneling at finite twist angle along the vertical c-axis of the junction. And this can lead to interesting macroscopic phenomena, quantum tunneling phenomena. Also, more recently, there has been some theoretical work, I also was in some of them involved, where basically, if you study the quantum coherent tunneling, you could propose that on the vertical axis of this Josephson junction, around some specific magic angle, you can have the mixing of these two order parameter, of this nodal order parameter, so that you get an imaginary component. And so at some specific angle or in some range of angle, and this is very difficult to quantify specifically for theory because DFT calculation requires some parameters that are also uncertain in experiments, then it happens that basically you could expect to have time-broken states in those systems. And not only, you can also realize spontaneously time-broken states or dynamic time-broken states, depending at which angle you are. So this means, for example, that if you have a nodal gap, you apply a current across your Josephson junction, and then you basically deplete the nodal gap, and you open a gap. Okay, so then the system completely changes. And these are dynamic state and spontaneously broken state are also what I'm going to discuss. First of all, realizing cuprates nano devices is difficult. It's really difficult. And has been for 30 years people trying to realize C-axis Josephson junction. Now, what is the big deal? So first of all, in plane Josephson junction has been realized. The way superconducting order parameter has been measured. And these junctions add Cooper pairs with a coherence length of 2 nanometers about. So you could be a little bit forgiven if you have some sort of disorder or meandering at the interface. But if you speak about the C-axis Josephson junction, which had all the interesting properties I'm speaking about, and people have for long tried to realize, then you have a coherence length of 0.1 nanometer, which means that basically for realizing devices, microscopic devices, you need to have angstrom precision. And now people have realized vertical junction using BISCO, for example, bulk crystal in the 1999, whisker junctions, and so on, and even recently thin flake. All these methods showed an approximate no angular dependence except of the critical current density, except for the case of the whisker, where however the cosine dependence that you expect from D wave was not very evident. All these methods showed that the junction, when they are realized, they are basically insulating. But what they do is to restore the superconductivity by introducing oxygens at very, very high temperature. So they have these kind of things in common. However, we know that cuprate material are very sensitive to millielectron-volt energy range and are very sensitive to oxygens. Cuprate, some of them, especially for example, some of them, like there are like lanthanum copper oxide, many others, but so they're oxygen ion conductors, so the oxygen are thermally mobile. And also, there has been measurement and experiment and theories that says that basically the topology, if you want to call like that, or at least the ordering of this K space, the K space ordering in real space of the oxygen in a material is very important for the property of your material itself. Last, the oxygen interstitial is one of the most vagabond of the elements that you can imagine on the periodic table, like hydrogen. And although it's recognized for the functionality of many complex materials, it's very difficult to control. For example, X-ray space mapping, like you see in this picture on the left, show how the K-space ordering of this oxygen interstitial in lanthanum copper oxide vary across a space of several microns. So the oxygen RK space orders are strongly correlated with the high temperature superconducting properties of this system. And you can also start to control this X-ray, this oxygen ordering if you put yourself close to the temperature when the oxygen starts to be mobile, which is 200 Kelvin. Then you apply X-ray flux, as you can see on the rear, and then you see this K-space wave vector related to the oxygen ordering increasing in diffraction. And then if you quench, depending on which stage of the order you are, the system at low temperature, you will see different TC and increasing with the K-space ordering of the oxygen interstitial. So you can control. So now Bibisco itself, so this is just to show how sensitive the system are to oxygen, how much important it is to understand deeply what the oxygen are doing. And so the Bibisco generally, as shown by Novoselov and others, can be stamped with a Scotch tape on a substrate and on thin limit, on two-dimensional atomic crystal, by breaking the bismuth oxide bonds. The problem is that when you do that, the oxygen basically boils in the system, and the system becomes insulating. More recently, we have done some work in two different groups. I've shown that you can isolate the high temperature superconducting atomically thin Bisco down to very, very thin crystals. And this shows that you can retain the maximum critical temperature for the case of bismuth 2212 of 90 Kelvin down to the very thin limit. Now, there are something that you have to preserve when you do that. First of all, it's very remarkable. This is an X-ray mapping done with a 50 nanometer beam on top of a very thin Bisco crystal. And you see the superconducting transition temperature. And on this right corner, you see a plot, an histogram, and you see that the variation, the sigma of the K-space order of the superlattice modulation when you are in the very thin limit varies only of 0.002. So this means that when you go to the very thin limit, the incommensurate modulation that we have heard before is really stable, is there, and doesn't change at all, or change very marginally. Now, so then we needed to develop new method to transfer this material, because the oxygen RK configuration, we know that must be frozen below 200 Kelvin, because above the oxygen are mobile, in order to preserve the ordering. And as well, we needed to preserve the lattice, like the incommensurate lattice modulation, from interaction with any sort of water molecule. Because in any possible situation, even if you are at high vacuum, you will have water molecule that will come and diffuse on top of your surface. We are talking about here about surface science, okay? So we developed some methods. So it turned out also by a matter of luck, actually I would say, that if you lower the temperature very much in an inert atmosphere, the PDMS becomes has a glass transition close to minus 123 Celsius. Now, most of the people that work on 2D materials, they generally realize the transfer and the stacking of graphene, TMDCs, and all the possible field that you can imagine in 2D materials is done with PPC, NPC polymers, which forms a liquid when they cross the glass transition, and then by freezing again, so this liquid encapsulates your crystal, and when you lower the temperature again, it freezes, and then you have enough force to tear apart your graphite in graphene flake, and so on and so forth. But if you do that with the BISCO, you will devastate your system, without mentioning that for doing this method, you have to use solvent, and solvent contains waters, so you are going to devastate twice your system. So you really cannot do any of this. So we know the oxygen are mobile before below minus 70 degrees Celsius, so it turns out that if you exfoliate the BISCO flake, use the PDMS, and the PDMS goes very close to its glass transition temperature without overcoming it, it becomes like a Scotch tape, really a Scotch tape. It becomes sticky like incredibly.
Nicola?
Okay, sure, wow. So then what you can do is to restack this system on top of each other and give a twist. This is impossible. Okay, but so this is so to understand how sensitive are these materials, you can see that if you have the interface exposed to the atmosphere and you use this method, then you, even though you see the same superconducting critical temperature, you will have very different Josephson characteristics. But if you encapsulate the system because you have high vacuum evaporator, then you can protect the system from water molecules, and you can measure 1.2 kiloohm per centimeter square as intrinsic Josephson characteristics. So I'm going a little bit fast. So you can realize this with different methods, with cryogenic transfer plus encapsulation in an evaporation at high vacuum, or with cryogenic transfer plus evaporation without encapsulation in ultra-high vacuum. You see, so then all the samples that we measured that are 30 more have superconducting transition around 90, strong hysteresis, and critical temperature that are, and critical current that are one of the intrinsic Josephson junction. If you look at the raw data, you can already see here in the dynamic resistances that there is some changing depending on, in this table, depending and where each plot is an angle. And now, if you look at the TM picture, you see the quality of the interface that we have realized of the supermodulation on top of the BISCO flake. These are atoms that you see, and where you see this modulation is basically where you have tear apart the crystal. And you see that the ICRN for different methods that we have used always show a D-wave dependence. And I very quickly finish because otherwise. So what happens is if you are at a specific angle around near 45 degrees, you can see very special state appearing like fractional Shapiro steps, so second harmonic modulation, so changing the current phase relationship. Also asymmetry in the Fraunhofer pattern and fast oscillation, as you can see here. Finally, in order to improve our method, now we are trying to go in a hybrid superconducting system, so we are developing another method to realize and in order to combine a very complex circuit. So for example, we can, sorry, I have to go fast because otherwise I don't finish. But, so we are working on this. Okay, so thank you very much. Yes.
Thank you very much, Nicola. Now, questions?
Technical question. You mentioned size C, coherence length in this direction being 1 angstrom.
0.1 nanometer.
So, yes,
Yes.
so it's 1 angstrom.
See.
So how do you know that this is it's extremely short?
Well, in literature, most of the time people, there is a very strong, not from my data, I know, but in literature there are several methods that shows that, I mean, people have measured these properties.
Okay, thank you. Over there.
Do you know something about broken of particle Hall symmetry in D-wave superconductors and the possibilities to realize for example, like diode effects, different diode effects. Can you comment on that?
Sure. So we have some evidence that I'm not showing here because it would be too long. And we are still measuring where you may have this kind of effects in the system. But at the moment, I just want to point the fact that we have some special effect around some angle, and we are trying to basically understand from where they come from.
Okay, thank you. Well, unfortunately, we have to move on to the next. Thank you very much, Nicola, again.
Thank you.
And